Hi class. Last time we considered asymptotic expansions of Laplace integrals of the form shown here in the case where phi did not have a maximum or minimum, it didn't have a critical point where phi prime vanished someplace inside the interval. So naturally, the next thing to consider is what happens when the derivative vanishes somewhere inside, say at a point C. Well, as you can see, if it has a critical point and is concave downward, as we've discussed here, it's going to be dominated. We expect the value of the integral to be dominated by the value of the maximum. If instead it were concave upward, it's possible you'd have to see the relative value of the minimum, the critical point versus the endpoints. It might be possible the integral is instead dominated by the endpoints, in which case essentially integration by parts will work because the minimum would be irrelevant. But let's consider the case where we expect the integral to be dominated near the critical point where the derivative of phi prime vanishes. So C is the value such that phi prime of C equals 0, and as drawn, we're assuming phi double prime of C is less than 0. So we're going to expand around the point C. So phi of t, we expand in a Taylor series. Phi of c, the derivative vanishes, plus the second derivative of phi of c with respect times t minus c squared, plus higher order. We're going to derive an asymptotic expansion by considering by ignoring the higher order terms. As x goes to infinity, again, we're doing the asymptotic expansion as x goes to infinity, the values of the parameter t that are going to dominate the integral are going to come to be closer and closer to t equal to c. So as x goes to infinity, we expect this integral to be dominated near c. Epsilon just denotes some small value, small positive value. We expand the function f of t around c, and then we expand phi around c. And the leading behavior is going to come from this term, the first term in phi. This term is just going to give an overall exponential function, and the integral is going to be dominated by this. So we expect that the leading behavior is going to come from f of c times e to the x phi of c times the integral around c of e to the x phi double prime of c of t minus c squared over 2 dt. As x goes to infinity, we expect that only the values of t near c are going to matter. So instead of actually integrating right around c, we can instead approximate this as a Gaussian integral near t equal to c. That, of course, is something that we have to check. There's a lemma, Watson's lemma, that allows us to show that this will give us a good asymptotic approximation. You can read about Watson's lemma and Bender-Nordtag in Chapter 6. But if we take that lemma as given, then the leading term of the asymptotic expansion comes from this overall expression f of c e to the x phi of c times this Gaussian integral. The Gaussian integral is easily done. You get f of c e to the x phi of c times the square root of 2 pi over minus x times phi double prime of c as x goes to infinity. Notice that this is different than what we got when we got integration by parts. In integration by parts, we got integral powers of x. The fact that phi had a critical point and its derivative equals 0 here at this point means that we get a different form for the asymptotic expansion. You get the same kind of leading behavior. You might have guessed this leading exponential behavior and constant behavior, but it falls like 1 over the square root of x because it's a critical point. We can actually use this to derive one of the most famous formulas in use in physics, especially in statistical mechanics. That is Stirling's formula. We'd like to understand how the factorial function n factorial behaves for large n. We do that by looking instead at the gamma function. We know that gamma of n plus 1, where n is an integer, is n factorial, where gamma in general for an arbitrary function, arbitrary value x, gamma of x plus 1 is the integral from 0 to infinity e to the minus t times t to the x. Now, this is not directly in the form of Laplace's form because it's not the exponential of x times some kind of function. In fact, if we write everything as an exponential, there's a dt missing, if we write everything as an exponential, you can see that what's sitting in the exponential is the function minus t plus x log t. Now, if we think about where this function has a critical point, we'll see that it actually has a critical point at the value t equals x. So it has a movable maximum inside the interval from 0 to infinity. But it has only one maximum where t equals x. So let's rescale our variable of integration. Let's let t equal s times x. If we let t equal s times x and plug in, as we did here, you'll see that we get an overall controlling factor, x to the x plus 1, times an integral that's of Laplace form. And now we can simply use Laplace's method as derived above, because we already know, in fact, that the critical point of this new function g in terms of s is just at s equals 1. So the value of g at 1 is equal to 1. Its derivative at 1 is equal to 0. And g double prime is just 1 over s squared, which is equal to 1. So we're going to approximate g as its value at 1. This is going to vanish. And we're going to get the quadratic approximation here. So gamma of x plus 1 is asymptotic to, well, we have the x to the x plus 1 over here. We have e to the minus x, and we just plug in the quadratic approximation for a function in terms of s, 1 plus s minus 1 squared over 2. And we can just do the integral the way that we did before. We get x to the x plus 1, e to the minus x, the square root of 2 pi x, or x to the x, the square root of 2 pi x, e to the minus x, which if we write it in terms of the way it's usually written in terms of Stirling's formula for integer n factorial grows like n to the n up to an extra factor of the square root of 2 pi n and e to the minus n. And now you can actually see how good an approximation Stirling's formula is. We've plotted here gamma of n plus 1, or Stirling's formula, as a function of n, and we've allowed n actually to be even half, 1, 1.5, 2, because we actually know how to evaluate the gamma function. And you can see it's an extremely good approximation. Stirling's formula is a very good approximation. It's very good even for n equals 2 or 3 for approximating the value of n factorial. This is one of the fundamental formulas that you'll see used all the time in statistical mechanics.